computer. Okay, and actually, I don't know why I didn't wait to. I don't know why I decided to start recording and then move, but I'm going to move just for 1 second. Okay. Um, you will have a quiz posted later today, and that's going to follow the same up for 26 hours as the other ones have. Um, but with that said, we are going to go ahead and get started. Today we are talking about ions. This is also a little bit of using what we talked about previously with the structure of atoms and kind of expanding upon it and kind of, applying some of that information. So this applies to, or this corresponds to sections 4.1 to 4.3. Let's get going. So, um, if you remember when we talked about the periodic table and the makeup of the periodic table, there were a couple of important pieces of information about the periodic table. I'm going to do a little sketch, a rough sketch of the periodic table at the top of this slide. And that looked a little bit like this. And I'm going to draw kind of fine lines to, there we go. And then there's this block down here. Now we had a couple of different ways of organizing it. We talked about it structurally, the basically the places that atoms were found or electrons were found in atoms. We designated this right here to be the S block, this to be the P block, this the D block, and this right here is the F block. Now, one other thing that we talked about was we talked about classifying substances as metals versus nonmetals. Now, when it comes to classifying something as a metal or non-metal, I think everyone kind of has a sense of um, like a tactile, a touch sense of like, okay, this right here, plastic. I know that it's plastic because it's not very hard. And okay, yeah, there we go. There, that's kind of my definition, my rough definition for a non-metal. This right here, well, that's actually a metal, and I know that it's a metal because of the hardness that it has, as well as maybe its ability to conduct electricity or its ability to conduct heat and transfer heat. Well, we also can look at conductivity. So here's a simple apparatus where we have a battery, a power source, which I'm going to label a PS, and that power source can have electrons flow from one end, from the positive end to the negative end, and electrons will flow through here and ultimately hook up with this light, and that light is going to be powered by this power source. So if we just had this going right here, then that light would be solely powered by the battery. Now, here, what we have is we have these little alligator clips that they can chomp onto material. And in this case, we have graphite from a mechanical pencil or just a wooden pencil. That graphite's been removed, or I think we all like to call it lead. That lead's been removed. And this is a test of, does this lead conduct electricity? And, is this light on or off? Now you can see if you look very closely right here, the light is on, but it's very, very faint. Meanwhile, if we go over here, we've got the exact same setup, but we have our electrons flowing through aluminum foil. Now, what you notice is this light over here that I'm going to label B versus A it's pretty safe to say, and it's pretty clear that B is more illuminated or is brighter than A. You're not wrong in that assessment. And that just goes to show that aluminum foil is better at conducting electricity than graphite is. Now, this all has to do with, in part, the organization of where different materials and different substances are on the periodic table, but also the number of valence electrons that they have. Now, as a little bit of a review, remember our valence electrons are outermost electrons. So those outermost electrons, different atoms or different elements have different numbers of those valence electrons. If you look at this row one or this group one right here, if you look at, say, sodium or potassium, these are both materials that have a total of one valence electron. Group two, right here, beryllium or magnesium, they have two valence electrons. Now, this part in the middle, or this part of the periodic table that's the middle, these are our transition metals. Those transition metals have varying numbers of valence electrons, and so it's not as intuitive. I apologize. It's not as intuitive to say, oh, this has this many valence electrons as it or when we're thinking about the transition metals. However, when we jump over here to this side of the periodic table, it's a little bit more clear. We can say this has three valence electrons, 4, 5, 6, 7, and 8 valence electrons. It's a little bit more, it's a little bit simpler to put it. Yeah, it's a little bit simpler. So if you look at something like chlorine, chlorine has 7 valence electrons. Xenon has 8 valence electrons. Tellurium has 6 valence electrons. Those are those outermost electrons. Now, each of those different substances have different numbers of total or different total numbers of electrons, but their valence electrons are those. Those are the outermost ones. Now, when it comes to our outermost electrons, those are the ones that are farthest from the nucleus. So if we were to draw an atom and say, okay, here's a nucleus, here's some electrons, here's some electrons. And then your valence electrons are going to be way out here and here. These electrons, like this one that I'm drawing a box around, it's pretty far from the nucleus. So it doesn't feel the pull of that nucleus. Now, to illustrate, so those valence electrons are critical, and those arguably are the most important electrons when it comes to understanding how a particular substance either reacts or acts around different chemicals. So, I apologize. What we want to do is we want to be able to draw what's known as a Lewis dot symbol to represent valence electrons. So I'm going to toggle back and forth between this slide and the previous slide. Here's our periodic table. Aluminum is right here. So I'm going to copy some information over here. Aluminum has 3 valence electrons based on it being in group 3. Now, how many total electrons does aluminum have? Total electrons. Well, we can figure this out by looking at its atomic number, 13. So it has 13 total electrons. 3 of them are valence. 13 total, but only 3 of them are valence electrons. Okay. Now phosphorus. Oopsies. Phosphorus is right here. Phosphorus has 5 valence electrons. Or yeah, it has 5 valence electrons and 15 total. 5 valence, 15 total electrons. Now, whenever we're drawing a Lewis symbol, we don't care about that. We also don't care about that. what we draw for a Lewis symbol is we have to take into account the number of valence electrons that an atom has, and then we place those electrons around the atomic symbol. So aluminum, for instance, is going to have a total of 1, 2, 3 dots around it. Phosphorus is going to have 5 dots around it. 1, 2, 3, 4, 5. The convention is that you start and you place one electron around or on each side. And then you kind of fill them in either clockwise or counterclockwise. So if you have so here what we have is phosphorus, for example. What I did was I placed my first, second, third, fourth, and then my fifth. Now we'll jump ahead, and here is a rundown of the periodic table or our main group elements. There's a little bit of a difference in the way that they did it and the way that I did it. I'm not going to really be splitting hairs on which one is correct or incorrect. Um, but you should, what I am looking for is I want you to treat each symbol, let's say BE, treat it as basically being in a box with 4 sides. And on those 4 sides, 1, 2, 3, 4, you're going to place electrons. So what would be an incorrect symbol would be something like this, phosphorus, 1, 2, 3, 4, 5. That would be incorrect. I don't want to see that. What differs between their phosphorus symbol right here and mine is the placement of that 5th electron. That's the sort of thing that I'm not going to lose any sleep over. You want to evenly distribute the electrons as much as possible, as is evidenced by, which is what you see with carbon here. Carbon has 1 electron on each side because there's a total of 4 sides, there's 4 electrons. Now, where you place the others doesn't really matter to me, but I want you to evenly distribute them as much as possible. If you're looking for a really good reference on what are kind of the standards to look at, use this slide right here. This shows a really great model for the Lewis symbols or the Lewis dot structures, as you might hear them known as or referred to as the Lewis dot structures of our main group elements. Now, I've got a Zoom poll here that I want everyone to go ahead and take care of, which I'm going to open it in just a second. Going to go with, there we go, it's launched. I'll give you a little bit of time to answer that. Give you about 15 more seconds on that. Go ahead and end the poll. Okay, so this was asking for the atomic symbol B for boron. Now, if we jump back, let's go through the process of, deducing how to put this together. Boron, right here on the periodic table, is represented by the capital letter B. It has 3 valence electrons. Let's jump ahead. So we're going to do 1, 2, 3. I see that the popular answers were 3 and 5. 5 is incorrect because we're not looking for the total number of electrons. We're looking for just the number of valence electrons. Okay. Now we can proceed from here. So what what was noted at the bottom of the previous slide was the octet rule, or what's the max number of dots? 8. If you look at your noble gases, which these are 18, these are farthest to the right of the periodic table. There's 2 electrons on each side. 4 sides, that gives us 8 electrons. So that rule tends to be true. You want to put no more than 8 electrons in a Lewis dot structure. And that has to do with a number of different factors, one of which is the likelihood of bonding that different chemicals have. But the octet rule is summarized as atoms tend to gain, lose, or share electrons until they have 8 valence electrons. So basically what this means is that an atom is going to gain or lose electrons until it reaches a total of 8 surrounding it. So if we look at something like our noble gases, helium is a little bit of an outlier. But let's look at neon, argon, krypton, and xenon. They have 8 electrons. So they're actually not going to lose or gain any. Group 7 atoms, fluorine, chlorine, bromine, iodine, by contrast. What they like to do is they like to find something that they can bond with that they get an electron from, because that gets them to 8 electrons. Now, if we think about this, let's pick out chlorine. Cl with 1, 2, 3, 4, 5, 6, 7. 7 valence electrons. Na has 1 valence electron. This note at the bottom is that these species in groups 1 and 2, and sometimes 3, they tend to lose electrons. Now, if sodium lost an electron and it went to chlorine, then chlorine has 8 valence electrons. And sodium effectively has the same electron configuration as neon. So it's almost like these guys over here on the left-hand side, they like to lose electrons because then that gets them to, it's almost like, I hope that it's almost as if, let's say that sodium's a basketball player in high school, and they're pretty good. They are a senior, they are on the varsity team, and they're a good player. But everyone else on the team is also very good. And the coach comes up to Sodium and says, listen, I know that you want to have 8 valence electrons, and I know that you want to play all, 48 minutes in a game. I know that you want to do that. I don't know what high school basketball times are, but I know that you want to play every single minute of the game. But I'm sorry, I can't promise you that. And that's just not in the cards. So I've got an offer for you. If you lose 1 electron, you can drop from varsity down to JV. And when you drop down to junior varsity, you will play every single minute. Sodium says, all I have to do is lose 1 electron. And coach says, yep, that's right. Sodium says, well, I love to play, and that's what I want to do. I don't care about being on varsity or junior varsity. I just want to play. And if giving up 1 electron gives me the chance to go and play, that's what I'm going to do. So sodium, what it likes to do is it likes to give up 1 electron. Magnesium likes to give up 2 electrons, calcium, 2 electrons, rubidium, 1 electron, and so on. And they do that so that they can effectively participate in some sort of bond, but it's equivalent to what they're going to take away from it is when they lose an electron, they have a noble gas E configuration. Then these guys over here the ones that gain electrons, will ultimately, when they do gain electrons, have a noble gas E configuration. So they gain or lose electrons to get 8 valence electrons, which is a noble gas electron configuration. Now, here's kind of the example that we looked at: sodium and chlorine. If you remember, we talked about sodium and chlorine early on. Sodium is highly reactive, and this is early on in the semester. Sodium is highly reactive in water. Chlorine is a gas and is potentially fatal to people. Sodium chloride, by contrast, well, you put that on salt or you put that on food and makes it taste better. In order for NaCl to form, sodium loses an electron. Chlorine gains an electron. Now, what we know from the periodic table, when we talk about a neutral atom, we talk about this guy right here, this guy right here. If we look at the periodic table, we see that sodium has 11 protons, and as its neutral atom self has 11 electrons. So Na, 11 protons, 11 electrons. Those positive charges right here, these negative charges here, effectively cancel out. The 17 here, 17 here, cancel one another out. Now, when sodium loses one of its electrons, so when a sodium atom goes down to JV, it goes from having still 11 protons, but now it only has 10 electrons. So it goes from 11 to 10. Now, if we look at this, we've got 11 positives and 10 negatives. Those combine to give us a charge for our species, which is +1. Chlorine, we've got 17 protons and 18 electrons. That's going to give us a charge of -1. So these are ultimately atoms. Now, this I always like to pick out because Lithium is a song by Nirvana. It's one of my favorite songs, and it's also a simple atom. Let's dissect this atom. So we have on our right here, we have an atom that consists of our nucleus, which is 1, 2, 3. So it's 3 neutrons, 1, 2, 3 protons. So that gives us 3 positive charges, 3 neutral charges, and then 1 electron, 2 electrons. So 2 negatives. So when we have 3 positives and 2 negatives, we end up with a positive ion. So when it comes to classifying an atom versus an ion, a neutral atom has an equal number of protons and electrons. So that means that our however many positives, let's just draw 1, 2, 3, 4 positives, are essentially combated or neutralized by 1, 2, 3, 4 negatives. A positive ion, or heck, a positive anything. You know that a positive anything has more positives than it has negatives. And you could translate this to, I always like to think of other sorts of examples or analogies. If you have an income of $10,000 a month, but then you have expenses of $15,000 a month, what is your financial statement at the end of that month? Well, 10,000 positive, 15,000 negative. Well, the 10,000 positive cancel out 10,000 negative, but you're still at -5,000. If you had a income of $15,000 and expenses of $10,000, well, then that would be a positive, a net positive. So when you're thinking about atoms versus ions, you have two different types of ions, either positive or negatively charged ions. A positive ion loses electrons. It has more protons, positives, than electrons. A negative ion. A negative ion is going to gain electrons. It has more electrons than protons. These are both known as ions, so that word is present in both of these, but you just have to account for, is it a positive ion or a negative ion? Okay, we got another Zoom poll here. I could just call it a poll as opposed to a Zoom poll. It's pretty obvious that it's a Zoom poll because we're in Zoom. Here, what we're going to do is launch this. How many dots surround Br minus and the Lewis dot symbol for Br minus? Competitive answers is what I'm seeing from my end. Give you another 10 seconds to think about this one and get an answer in. Go ahead and end it. Okay, so the correct answer is really between 7 and 8. The correct answer is C. Now, the tricky part about this is this right here, that negative, is significant because if you have this is really it's Br versus Br minus. Are they the same thing? And it's pretty safe to say you can look at it and you can say, okay, well, no, they're different because one of them has a minus and one of them doesn't. Okay, great. Now that minus indicates negative. So this is a negative ER. This is neutral BR. So as a negative BR, this has gained an electron. And I think most people probably look at the Lewis structure for Br and say, okay, it has 7 valence electrons. Great. Now, what if it's Br minus? Well, that means it gained an electron, so that means I'm going to draw in a total of 8 electrons. Now, what I want you to recognize also is if we say something like Mg versus Mg2 plus. Actually, I'm going to do some erasing real quick. Mg versus Mg2 plus versus Mg plus. Are those 3 different things the same? No, they're not. 2 of them are positive ions. Okay, so we got this as neutral. These 2 as positive. Now these 2 species as positive ions, Well, they're obviously different. That number 2 there is not a mistake. That means this one has lost 2 electrons, and this one has lost 1 electron. That is significant, and that is important to understand the differences between these three. So whenever you see a question like this, definitely account for what's the charge. Oh, okay, and now next question. Right, just a second. Okay, here we go. How many total electrons are in Br minus? Okay, another 10 seconds on this one. We'll stop it there. Oh, it's a dead heat. We got 4 and 4. So total electrons in Br. Now for this one, what I'm going to do is I'm going to bounce back to the periodic table. Br has a total of 35 protons. Yes. Now, so that means that it has 35 positive charges, and as a neutral bromine, it also has 35 negative charges. When we're talking about, however, this right here, Br minus, well, this is the 36th electron. So our correct answer is D. Okay. Now, this is just a nice list of, I'm going to stop my share there, of all of the very common ions that you should be familiar with. Um, these will primarily show themselves in uh, either explicit questions like what is the common ion for chlorine? That would be Cl minus. But one thing that I want you to notice sort of as a trend is that all your group 1 right here, atoms, what they like to do is they like to form +1 ions. So they like to lose 1 electron. Group 2 atoms, they like to lose 2 electrons. So they form +2 ions. The center of the periodic table, I think that you can see one of the reasons that we've been kind of, I don't know if I would say avoiding it, but yeah, avoiding, ignoring, whatever. Iron, it can form a +2 or a +3 ion. Copper can form a +2 or a +1 ion. Zinc +2, silver +1. Aluminum +3. The numbers of ions and the differences of ions is definitely not as apparent. Whereas group 5, 6, and 7, they like to gain 3, 2, and 1 electron, respectively. So those are our common ions that you should expect to see or that you should be familiar with. Okay, here is our last Zoom poll. What is the charge of the ions formed by group 1 elements? Ten seconds for this one. Poll now. Share the results. Well done. Everyone got that one right. All 8 participants got that right. I'm going to stop the share now. And I like to look at group one elements because that's where I can think of something like lithium. We previously looked at a model for lithium, and that model for lithium had our protons and neutrons in the middle. So P, 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 N, N, N. So there's our nucleus. Then we have an electron, we have another electron. Okay, and these are in this nice little ring surrounding our nucleus. Now, this right here is a +1 ion of lithium. So that is the form of lithium that is most commonly going to be found, where it has lost a single electron. Now, another electron way out here. I I, I have I don't know if it's a problem necessarily, but I do have a tendency to use kind of folksy and cutesy examples, and I was going to use them, but I'm not going to. Uh, let's imagine that the way that I always like to think about this is your protons, they have positive charges. They are attracting negative charges. And essentially, this is like when your protons and neutron or your protons and electrons, when they are equal to one another, that's almost like uh, playing, it's like man on man or person on person defense in basketball. So these three protons in the nucleus, they can kind of contain these electrons, and they can do it pretty easily. If this third electron right here was right here, then they could probably do that as well. But part of the work that was done, remember last week when we looked at those images of the line diagrams or the different colors, the emission spectra, where you had all those different colors from hydrogen gas or something like that. You'd have these electrons that aren't in the same place. And instead, some electrons are at super high energy levels and some are at lower energy levels. So this electron and this electron are at a low energy level. They're close to these protons. This third electron is way the heck out there. These protons are kind of contained. They are stuck in the nucleus. They can't leave. This electron way out here, this third electron, effectively, it's not being very well contained by the protons, by the nucleus. And so what it means is that this electron, it can just sort of dip out and leave. It can be like, listen, I'm not even close to the nucleus anyway, so I'm just going to have to leave. So see ya. So that's effectively a simple characterization of what's taking place here. The charges that are formed by these different group one elements are a result of basically where these different electrons are. So you've got two close electrons and one distant electron. That distant electron, gone. See ya. I'm out. Because it's not being very well uh, captured or contained or retained or held in or whatever by those protons. So our correct answer for this one, +1. Okay. Well, that's going to wrap it up for today. Tomorrow, we're going to continue on with chapter number 4. You have a quiz over today's material that will be going live today at 12 noon and will be up until tomorrow at 2 p.m. If you have any questions, please don't hesitate to contact me. I'll get back to you as soon as I can. Other than that, I will see you tomorrow at 10 a.m. I'm going to stop my recording.